matter. This kind of topological phase of matter, the topology cannot be defined without symmetry. Only in the presence of symmetry, we can see some kind of topological properties that are protected by the symmetries. For example, if you look at entanglement in the many-body wave function, there are some kind of short-range entanglement that is protected by the symmetry, which means that it cannot be removed without breaking the symmetry. And another kind of protection by symmetry is the stability of edge modes. That's probably more experimentally relevant. For example, in the edge mode of two-dimensional topological insulators, and we know that in that case we have a pair of counter-propagating edge modes, and you can describe them using one left-moving fermion and one right-moving fermion. But because of the time reversal symmetry acting in a way such that it prevents a backscattering term, so backscattering between the two edge modes cannot be added into perturbatively. So these edge modes are stable against any time reversal symmetric perturbation. And this kind of symmetry protected topological phases, if you generalize to many other symmetries beyond time reversal, like crystalline symmetries, or even in superconductors, and more generally spin conservation, etc., then you have a large class of symmetry protected topological phases. Another kind of quantum phase of matter is that studies the interplay between topology and symmetry is the so-called topological phases enriched by symmetry. These quantum phases of matter, without symmetry, even without symmetry, you are already able to define some topological property. For example, the most well-known is the fractional quantum Hall state. Okay, in this fractional quantum Hall state, these are two-dimensional electron gas, and you apply magnetic field, very strong magnetic field, and the electrons form a gapped many-body state. And in these systems, you can, if you study them, you find that, oh, there are some particle-like excitations called anyons, and they obey fractional statistics. These are statistics beyond the usual boson and Fermi statistics. It has been studied more than 40 years, I think, they are actually heavily sought, trying to because they can be used to realize so-called topological quantum computer. Okay, that's a property of these anyons, topological order systems. In the absence of symmetry. In the presence of symmetry, these anyons can also carry some interesting symmetry properties, for example, the fractional charge. I guess many of you, like Bo, is also working on a fractional quantum Hall state and trying to theoretically compute certain properties of fractional quantum Hall state, and trying to identify the topological nature of these states, and one of them involving the fractional charge. Fractional charges, for example, in the very famous Laughlin state as filling factor 1/3. Okay, 1/3 is one of the it's the first fractional quantum state that is ever observed experimentally. And there are actually two kinds of non-trivial anyons, and one is the trivial one, and the other two, and they carry fractional statistics, which is 2 pi over 3 or 4 pi over 3, but also they carry fractional charge of an electron, okay, 1/3 of electron charge. This fractional charge is the quantum number, fractional quantum number associated with particle number conservation, this U1 symmetry. So generally speaking, if you're trying to study, anyon systems, topological order systems in the presence of symmetry, then you can study symmetry fractionalization, okay? So of any symmetry G, okay? So there's this rich interplay between symmetry and topological order, so-called symmetry-enriched topological phase of matter. Okay, both of these topological phases, whether protected by the symmetry or enriched by the symmetry, has been studied for almost maybe last 10 years, and people trying to come up with a general framework, general characterization, classification of these topological phases. But there's one aspect is that symmetry and topological order may not always be compatible. In the sense, let me start with an example to show you what do I mean by symmetry and topology. They are actually incompatible. So the best example is actually integer quantum Hall state or Chern insulator. And we know that Chern insulator is characterized by a Chern number or equivalently by the a chiral edge mode, okay, a mode. So if we apply a time reversal symmetry, we know that the edge mode, the direction of the edge mode is reversed. Equivalently, the Chern number gets a minus sign, okay? So if we want to impose time reversal symmetry, then the Chern number must be 0, okay? In other words, Chern number with a non-zero, Chern insulator with a non-zero Chern number must break time reversal symmetry. Okay, this is probably the most well-known example of incompatible topological symmetry with a given topological order. And more generally, in fact, any kinds of chiral topological order enforces the time reversal symmetry to break, because we have actually a topological invariant similar as this Chern number. It actually can be defined physically and more generally, the so-called thermal Hot conductance, which is similar as the usual Hot conductance, but instead of an electric charge current, it's actually energy current. You apply if you apply a temperature gradient along, say, y direction, then you measure the heat current along x direction, then you can define this thermal Hot conductance as a kappa xy. It is proportional to up to some constant, okay, multiplied by a number c minus. And in the case of integer quantum Hall or Chern insulator, this C minus is the Chern number. But more generally, for so-called abelian topological orders, these anyons, they are abelian fashion. So this is always an integer. But more generally, for non-abelian anyons, which are actually building blocks of this topological quantum computer, this C minus can be a fractional number. For example, the well-sorted 5/2 state in quantum Hall state, the C minus is always a multiple of 1/2. Okay, so and this thermal Hot conductance is also odd on the time reversal symmetry. So any topological order with a non-zero thermal Hot conductance must break time reversal symmetry. So this is this gives a quite a general family of topological orders that are enforces the time reversal symmetry to break. But such a enforced symmetry breaking is actually not just limited to time reversals to chiral topological order. For example, let me construct one kind of artificial example that is a two-layer non-chiral bosonic quantum Hall system with filling factor 1/2 and minus 1/4. So this one is just like this is a bosonic because bosonic quantum Hall system is kind of simpler, so I choose it to be an example. And this is very much like the Laughlin state, and at a filling factor 2, but it's an even number, so it's bosonic. And this is also a bosonic topological order. So, and I choose this one to be a minus 1/4 filling factor, so that when you adding them together, the chiral central charge, okay, the thermal Hall conductance that I defined in the previous slide is actually 0. But you can find that this kind of a complicated topological order is incompatible with time reversal symmetry either. It's actually not hard to see, because in order to assign a time reversal symmetry in this topological order, we have a few conditions. The system a few conditions should be satisfied. For example, one of them is some anion x gets transformed to another anion. Let me denote it as Tx. And if we apply it twice, then we must go back to, because time reversal square is 1. Okay. And at the same time, time reversal is anti-unitary. So these are the numbers that I listed here, actually the exchange statistics of the two identical anions. So this exchange statistics of A is the fundamental anion in the layer minus 1/4. Okay, S is the fundamental anion in the filling factor 1/2. And these exchange statistics must get complex conjugated because of the anti-unitary nature. So now if you impose these conditions, and you see that this condition implies that the only possible time reversal action is you permute you send S to SA square because of this I and minus I. There's no other anions with exchange statistics plus minus I. And then you have this action. And also for this anion A, you're going to send it to either SA or SA square because of these exchange statistics. They are complex conjugate of each other. With these conditions satisfied, then you find that you can conclude that the first condition cannot be satisfied. Okay. There are two possibilities. You send A either to SA or SA cube. So that means there's no way that you can assign a consistent way such that this topological order is compatible with time reversal symmetry. And in fact, for any general topological order, and if you want to study the compatibility between time reversal symmetry and this non-chiral topological order, the criterion, explicit criterion, is not known yet. So here I'm just constructing example to show the possibility, but generally it's not that as easy as the chiral topological order, where one can define a topological quantity, this thermal hot conductance. But here I don't know what quantity I can define so that it can directly tell you that the time reversal symmetry and this non-chiral topological order is compatible or not compatible with time reversal symmetry.
Can I have a quick question about the previous slide?
Yeah, sure.
So for this bilayer system, you still have the chiral edge current, right? Chiral edge states, because it's 1/2 and negative 1/4.
Yeah, only if you define electric current. Electric current, yes, but the thermal hot conductance is 0.
Okay.
For any
is 0, yeah.
For chiral topological order, regardless the filling factor, it's always 1,
yeah.
or this one is always -1. So when you add them together, it's 0.
So you call it non-chiral basically because the thermal Hall conductance is 0. Normally we call this not maximally chiral, but still kind of chiral.
Yeah. So when I say non-chiral, I really only mean kappa xy equals 0.
I see. And for example, if you have a strained graphene, you can have a pseudo-magnetic field. Then you have a Chern number equals to 1 at K point and Chern number equals to -1 at negative K point. So this is a case where you do not break time reversal symmetry.
Yeah.
You still have 2 edge currents. The charge current is 0 because they have opposite direction.
Yeah.
But the valley current is kind of non-zero, right? In some sense, this is called barytronics. So do you still call this a topological, it's not a chiral topological order anymore? Is there any symmetry breaking in this case?
No, that's symmetry protected topological phase. So when I say incompatible topological order and symmetry, so first of all, in the absence of symmetry, you must have a topological order. Okay. I will be more careful about what do you mean by topological order. So first of all, you should have a topological order before you add a symmetry. Then you study the compatibility between them. And the symmetry protected topological phase, what you are mentioning is actually belonging to the first class symmetry. In the absence of symmetry, there's no topology. You can't even define any topology there. Topological properties.
So here the symmetry you're referring to is the time reversal symmetry.
Yeah, time reversal symmetry at this moment.
Okay. I suppose if you add a magnetic field, you still can have some kind of Chern insulator for the strain graphene. You can have strain and the magnetic field.
Yeah.
Right. It is still a topological insulator.
But
you can still have a valley current, for example, and also a charge current. Without the magnetic field, there's no charge current, chiral edge charge current, but there is still a valley current in some sense, right? So if I talk about the valley current as something kind of topological, then with or without the magnetic field, I always have a valley current.
Okay. But that's you assume there are a valley current conservation. In other words, you have 2 valleys, right? The particle number of both valleys are conserved.
Yes.
So that's an extra symmetry you are adding.
I see. Okay, sure, thanks.
So anyway, what I'm talking about is that, so this actually back to what you are talking about. So let's consider some kind of topological order. Okay, this may be, say, a Laughlin state, or this 1/2 bosonic topological order, or maybe Chern insulator or whatever. So it's a phase, right? So that means in this phase, there are many, all kinds of states. Then you ask a question. So imagine that every dot, maybe in this phase diagram, every point in this phase diagram is a state, but they are all belong to the same topological order before we consider symmetry properties of this state. Then when you add a symmetry, then generally you have a richer phase diagram. Okay, as here I'm showing a rather abstract phase diagram. So, but this phase diagram, first you have two regions. One, so depending on what symmetry you are considering. So one region is the symmetry is broken. Okay, another region is it's symmetric, but but the symmetry may act in different ways. So you've got different SET phases, symmetry-enriched topological phases. So you may have SET 1, 2, 3, or 4. Okay, that's a general kind of scenario that we can have. And people have been studying all these symmetry-enriched topological phases in the last 10 years. And I was mentioning this enforced symmetry breaking. But actually, what I really mean is that in this whole phase diagram, enforced symmetry breaking, and so this incompatible case really means that you can't find even this region, the symmetric region is actually a zero. There's no such region that is, you cannot find even a point in this whole phase diagram that the symmetry that you are considering is compatible with the topological order. So by incompatible case, I really mean that in the whole space of this topological order, all the states, it's not compatible with the symmetry. So everywhere breaks the symmetry you are considering. Okay. So so far I have been using time reversal symmetry as an example to show this incompatibility. So, but now you may ask the question, okay, any other symmetries that can be enforced, incompatible with some topological order? Okay. So we need to specify what symmetries we're going to consider and also what topological orders we're going to consider. Then they may be incompatible. Okay, and incompatible means that we need to go through all the states in the whole phase diagram. So, but actually, this incompatible case hasn't been widely studied because there are preconditions for incompatibility to occur. This precondition is that the symmetry that you consider must have a non-trivial action on the Hilbert space by its very definition. Okay, so because if by definition there's no non-trivial action, then we can always assign a representation of that symmetry in the Hilbert space as an identity, even though it's a rather trivial symmetry action. So, but it actually at least shows that you can find one state and the symmetry acts rather trivially. Okay, then it's a symmetric state, but it's okay. So it at least shows that they are compatible. That means in this abstract phase diagram that I was showing, you find one point. This symmetry G, general symmetry G, is compatible with this any kind of topological order that you are considering. So actually there are not that many symmetries which by its very definition has non-trivial action, but almost all of them are physically very important. So one of them is actually time reversal symmetry. Time reversal symmetry has, by its very definition, because it's anti-unitary, so it must sense this coefficient I into minus I. Okay, this action is by definition. And another thing is a mirror reflection. Mirror reflection has a non-trivial action by the fact that it changes the orientation. Suppose you are trying to study braiding. Okay, if you take a mirror, then clockwise becomes counterclockwise, and this orientation is built into many-body Hilbert space. In single particle Hilbert space, there's no orientation defined in. But suppose you have a many-body system, say you consider two-dimensional quantum Ising model, then you have a lattice, so you know what is left-handed, what is right-handed. But this action is not trivial, but in the very definition of mirror symmetry. And another non-trivial symmetry is a symmetry with non-trivial action is fermion parity. So if we consider fermion systems, then there is an operator which I denoted as PF. It acts on the states in the fermion system in a way that if this state contains even number, the action is 1. If it contains odd number, it's -1. So in general, we have this kind of action. It depends on the number of fermions. So NF denotes the number of fermions on this state. Okay, these are the kind of common symmetries that, by its very definition, it has a non-trivial action on in the Hilbert space. And more generally, you can study a general symmetry that contains this time reversal, mirror reflection, or fermion parity. Maybe there are some others. This list is not complete, but then you can contain some of them as part of your total symmetry group G. Okay, so then this total symmetry group G may also be enforced to break it, if not completely, partially maybe, if not completely. So that's the preconditions. And in this talk, I'm actually focused on the fermion parity. So let me, I'm going to focus on fermion systems. So let me explain a little bit in the case that, because my talk is going to be in some sense more theoretical. So I'm going to maybe explain a little bit about this fermion parity. And most of you already know that, but probably didn't realize the importance of this fermion parity symmetry. So when we write down the Hamiltonian of fermion systems, we always write down, say, a hopping term, Tij, Ci dagger, right? Or maybe some two fermions interaction, or it involves four creation annihilation operator, or maybe more generally, abstractly, we have a four, CCCC, for annihilation. Or these terms are artificial, more artificial, not kind of physically relevant. But in principle, you can always add them, either perturbatively, effectively, or say from some low energy effective theory. But you can never add an odd number, say only a single C, or odd number of a product of odd number of C's, because these terms violates the so-called locality because of the anti-commutation relation between fermions. Okay, fermion operator C. So we always only add terms with even number of creation annihilation operators. So that makes the fermion number conservation, fermion parity conservation. So you can define this operator, PF equals -1 NF. NF is the particle number operator. It's a sum over all the C dagger C. Then it must commute with this Hamiltonian. Any Hamiltonian with any coefficient you can think of, and it must commute with Hamiltonian. Also, in general, if you are considering any other symmetry which has a representation in this mini-body Hilbert space, then it must be commute with this fermion parity, because in general we are considering usual symmetries. So this fermion parity basically counts the fermion operator inside this operator, and if it's odd, then it's actually a supersymmetry. It's not the regular symmetry. It's a supersymmetry. So we require it to be symmetric. So that means this fermion parity, if you have a symmetry group, it's in the center of the symmetry group. Now, examples. So a general symmetry is we need to consider embedding of this fermion parity. Okay. So for example, the familiar ones like particle number conservation, which is U1 symmetry. So it's if you write down the operator, it's exponential I theta NF. Theta is between 0 and 2 pi. And the fermion parity is the element with theta equals pi. Okay, theta is the one that this one, right? So this is when I use this subscript F, which actually means that this fermion parity is properly embedded into the total symmetry group. And also you can consider spin rotation. Okay, SU to F. Okay, it is the usual spin rotation. You have a Pauli matrices, sigma x, sigma y, sigma z. When there is because spin 1/2, so you have a 1/2 here, and the fermion parity is actually also embedded as the z component of the spin. Okay, when theta equals 2 pi instead of pi, because we have this 1/2 here. So when theta z is pi and also theta x y equals 0, that you reduce this element, it becomes the fermion parity. So that's how we actually. If you want to be rigorous, how you need to specify a symmetry and in fermion systems. So this fermion parity embedding is important. Let me see. Okay, a bit slow here. So let me speed up a little bit. So these are basic concepts. So so for general symmetry, so in general, we need to specify how we embed this symmetry into the symmetry group. We need to use the so-called second cohomology group when there is the rest of the symmetries form a group G. Then we specify a two cocycle in this notation. Roughly speaking, it is a function, a Z2 valued function. Okay, satisfies some condition, the so-called cocycle condition, and up to certain equivalence. This equivalence relation gives isomorphic GF. So it doesn't. So that means we only need to consider equivalence classes of this of these two cocycles. So once it's specified, the group action in GF is specified by this multiplication. Okay, so G sigma is 0 or 1, and the little g is or H is a group element in big G. For examples, if we consider the simplest case, the G without F is Z2, let the group element to be 1 and G, then there are two possible embeddings or extensions of this G by the Fermion parity. One is you set this 2 cocycle, the group element lambda GG to be 0, then we have this symmetry group Z2 cross direct product of Z2. If it's 1, then we have a Z4F. It's actually so you see these extensions, they are quite different, look like the group wise. So, but this G is the same, it's always Z2. So with this specification on the symmetry group, fermionic symmetry group GF, so I'm going to study like how this in fermion system, this general symmetry group GF can be enforced to break by some topological order. And but in general, it's too hard. So I'm going to focus on a special class, the so-called invertible topological order. The name, while it sounds maybe not familiar to you, but actually, I guess most of you know what, in terms of examples, you know what this means. But by definition, what invertible topological orders I want to define is so given a topological state, say a topological order A, so by saying it's an invertible case means that we can find another phase, A bar. When you stack them together, you find that when they combined, it's actually a trivial state. So there's no topological order at all. That's before we consider symmetries. So that all immediately says that invertible topological order does not support anion. So if suppose you have anion in A, then when you stack them, you always have anion A. So anions in the two-layer system, it cannot be trivial. So for any topological order with anions, then okay, it's non-invertible. Okay, but there are something, many body entanglements cannot be removed by closing the energy gap. So it's still true even in invertible topological orders for a single one. So while it sounds like this sounds strange, what do you mean by a topological order without anions? Actually, the examples are all well known. It's all classified. So in fermion systems, fermionic invertible topological orders, so you can consider in low dimensions, 0D, 1D, 2D, 3D. 3D there's none, so it's trivial. But in 2D, the invertible topological orders are believed to be all these P plus IP superconductors. So P plus IP superconductors, it's chiral, right? It's chiral. And even without any symmetry, you cannot, this chiral edge mode cannot be destroyed. So it's actually a topological order in this sense, but it does not support anions. Now in 1D, that's the K-type Majorana chain. This Majorana chain is also topological order in this sense, because if you define it on an open chain, you say, oh, can we remove the Majorana zero mode at the end without, violating some locality or these very, very basic principles, then it's very stable, even regardless whether you consider symmetry or not. So for fermions, so for 0D, it's actually this part fermion itself. So this is all well known actually. For bosonic systems, there is in 0D, 1D, and 3, it's all trivial, but in 2D, there is this so-called E8 state. It's more exotic, but roughly speaking, you can think of that as 16 layers of this fermion P plus IP superconductor. This is, I don't, maybe some of you heard of the K-type 16-fold wave classification. So this bosonic E8 state is so if you stack it with the trivial fermion state, then it becomes topologically equivalent to 16 copies of P plus IP superconductor. But these bosonic systems, if we want to study the compatibility between this E8 state and any other symmetry, it's actually quite simple. For any anti-unitary symmetry, they are enforced to break because they are chiral state. And for any internal symmetry, they are compatible because there's no other symmetries if we consider internal symmetry other than mirror reflection or these things. So then they are all compatible because these are bosonic systems. There's no non-trivial action built into the definition, right, in bosonic system. So the rich physics actually should be, we should look for is actually in fermion systems, fermion. So in the rest of talk, I'm going to focus on 1D and 2D of fermion systems, fermion invertible topological order. So let me start with the 1D K-type Majorana chain, and we ask a question: this topological order, whether it's compatible with any GF. Actually, you can obtain a general criterion. So the criterion was actually already obtained in Fikowski and K-type's original paper of when they classify one-dimensional fermion SPT phases. But let me because this argument is actually not that rigorously, maybe involves something some complicated mathematics, but the general idea is simple, but somehow not many people know it. It's buried in some one or two paragraphs of that paper. So the claim is that for a general, let me focus on a finite group at this moment. G is not a continuous group. It's just a finite group. So any finite group GF is enforced to break by this Majorana chain if and only if this lambda that I was saying is non-trivial. As long as it's non-trivial. Non-trivial in the sense that it's not direct product of this G cross Fermion parity Z2F. So the proof is actually can be the general skeleton can be simply summarized by these three equations. So if you we can prove it by contradiction. Okay, I'm not sure if it's contradiction, but sounds like. So assume that we have a finite group GF that is compatible with the Majorana chain. So in this Majorana chain, we have a Majorana zero mode, which I denote as Z at the endpoint. So in this case, we have a twofold degeneracy. Okay, one ground state 1 and ground state 2, they differ by a fermion. So this Majorana operator Z, let's consider one Z at one end, and some symmetry, which may have a representation in this effective Hilbert space that is living on one end. So this Majorana operator, first of all, it commutes with the Fermion parity because it's a Majorana operator, it's a fermion operator, so we got a minus sign. And second, it has a property that it's actually commutes or anti-commutes with any other symmetry operators, because it has a property that it belongs to the center of this algebra. So it may commute or anti-commute, but let's denote it as use this mu g. It may be 1 or -1. Okay, it may be 1 or -1. So we don't know so far at this moment whether it's commute or not commute. But so we denote it as mu g. But then for the element g multiplied by gp, so because this is a representation, so we can split it off by p. So because p is anti-commute with f, so we get an extra minus sign. So that means that we can pick one g prime out of every pair g and gp, so that one of them must be 1, right? Mu g and minus mu g, one of them must be 1. So let's pick the one with mu g prime equals 1. And collectively, all these g prime form a subgroup. Okay, this subgroup is actually isomorphic to this. I denote it as g prime. Okay, so then because this fermion parity is central in the total symmetry group, then mathematically you can argue that it must be direct product of them. Okay, this is due to the property of the existence of Majorana zero mode. So we got this criterion for 1D symmetry, enforced symmetry breaking. Okay, so the symmetry group is enforced. So in this case, the direct product case means that this lambda is trivial. Okay, that's the simple 1D case, and the simplest case is Z4F, the example, because this is a non-trivial extension of the Fermion parity. So for the 2D case, 2D case, the classification is more complicated. So we not only have a single Majorana chain, we actually have many of them. So we can let me use the one index nu to denote the topological. It's chiral, but now here it's chiral. So if you study time reversal symmetry, then there's incompatibility issue. Compatibility issue is easy to understand, but we're gonna study unitary symmetries. So so there are different cases we need to consider. So for example, nu equals 1, that corresponds to P plus IP superconductor. nu equals 2, nu equals 4 bilayer, and up to nu equals 16. There is a 16 periodicity, actually. There are some properties we can argue. For example, all the anti-unitary symmetries are broken because of chirality. It's very simple. So we need to focus on unitary symmetries. And also 16 copies of P plus IP is equivalent to bosonic E8, but bosonic E8 is compatible with all the unitary symmetries. So we actually only need to consider nu from 1 to 16, or modulo 16. So with unitary symmetry, so I'm going to show you that we can define a triplet to describe the so-called symmetry-enriched invertible topological order, because now once we want to add some symmetry, we need to describe how to we need some data to describe how the symmetry interact with this invertible topological order. And this nu is this nu, which indexes the the intrinsic topological order. And there are two functions, N1 and N2, which I will describe in a moment. And they can be defined quite physically. And building on this data that one can define, one can construct some so-called abstraction functions. Basically, these are consistency conditions that these data must satisfy. And the enforced symmetry breaking criterion. So when incompatibility occurs, or when enforced symmetry breaking occurs, can be stated using these 01, 02, 03, 04 so-called abstraction functions. These abstraction functions are functionals of all these the 5 elements. So G lambda describes the symmetry, nu describes this index, and 1 and 2 I'm going to define in a moment. So that's the outline of the next few slides. So in the case of, so I need to specify, the discussion will be separated into the case for nu equals odd, and nu is an odd number and nu is an even number. Let me start with the nu is odd. To study, first of all, as I said, I need to define these two data, N1 and N2. So let me first define what is N1. But you will see that after I define N1, the criterion for enforced symmetry breaking with odd nu is almost there. So how to define N1? It's defined by, we insert some symmetry defect, okay? So because now we assume that this let's assume that this new invertible topological order with index nu is compatible with the total symmetry group GF. So we can insert an defect G. Also, we can insert G. Let me denote little g as an element in this G without subscript F. So we can insert all these defects. And on each defect, we may or may not have Majorana zero mode. Oh, by the way, first of all, the Fermion parity along P carries Majorana zero mode, right? So when we have an odd number, when this index nu is odd, that means we have odd layers of P plus IP. So this Fermion parity carries a Majorana zero mode, depending on nu mod 2. So now when we insert this defect, we can also ask the question whether this G defect carries Majorana zero mode or not. But in general, we don't know, right? Whether it, so we use this function N1G to denote. This one has some meaning so far. This one literally just means that it only depends on one group element. So it only depends on one group element, and this value can be 0 or 1, denotes whether this G defect carries Majorana zero mode or not. So, but because the Fermion parity P carries Majorana nu, so you can say that N1GF is NG plus nu, or more compactly, if I denote GP as, so this sigma is 0 or 1. G0 is simply G, G1 is G times P. It's a more compactly, we can write it in such a form. Okay, so this N1G denotes whether this G defect carries Majorana zero mode or not. But this Majorana zero mode should be compatible with group multiplication. So if this G defect, G sigma, when it fuses with another H defect, it must be come up with, according to the group multiplication law that I defined using this lambda. So it must satisfy this, respect to this group multiplication. Then you add the Majorana zero mode on top of that. Majorana zero mode, or maybe put it in another way, is that the Majorana zero mode, when you have two Majorana zero modes, when you fuse them, you got none. So there is a fusion of Majorana zero mode, but there's also this group multiplication. Then from the compatibility between fusion rules of the Majorana zero mode and the group multiplication law, then we got this consistency condition. So this is simply, you count the Majorana zero mode on the left-hand side and right-hand side, and you got this equation. Okay, this equation, so you got N1G plus N1H minus N1G. So this plus minus sign is not that important because everything is going to be modulo 2, but this is more conventional. So nu times lambda GH. Write it more compactly. Let me define a quantity called O2, which is the right-hand side of the equation in the previous slide. And dN1G is the left-hand side. Okay, so this is simply the same equation. This is, I will denote it dN1. This is O2. So now, if you look at this this equation, for the case nu is odd. So nu is odd means that we can just simply set nu equals 1. So lambda is actually a 2 co-cycle that I defined. But on the right-hand side is actually this 2 co-boundary. Okay. So what this equation says that a 2 co-cycle is equal to a 2 co-boundary. This is not always true. Mathematically, this is not always true, but physically we require it to be true. So that now we arrive the criterion for odd nu, that GF is enforced to break by 2D invertible topological order with the odd nu if and only if this lambda is trivial, because the right-hand side is a co-boundary. Okay, so people may, so this is a simple criterion that we can say for nu equals odd. And the people may realize that this criterion is the same as the Majorana chain, okay, in 1D. Actually, it's not that surprising because there is another argument that one can give by dimensional reduction. Suppose you have a 2-dimensional sheet and you put it on a cylinder, then you insert a fermion parity flux, because for odd nu, the fermion parity flux carries Majorana zero mode. So you actually have a zeta zero mode at the end, both ends. So if you do dimensional reduction, you reduce it to 1D Majorana chain. So by similar argument in the 1D case, you obtain actually the same criterion, even though the physics behind these criterions are slightly different. So that concludes my case for odd nu. For even nu, this obstruction O2, okay, it's trivial because it's even. So all these equations are modulo 2. So this O2 is trivial. So there's no so 0 is the co-cycle. Is a co-boundary. So this equation always have solutions. So for even nu, we need to, in order to obtain some criterion for enforcer symmetry breaking, we need to define an additional quantity, the so-called N2. And then it depends on the 2 group elements. Okay, this N2. So in that case, for nu equals 2, what one needs to study is you consider that every defect, there are different cases. So the first, for the odd nu case, I already said that one property of a defect is whether it carries Majorana zero mode or not. But now let's focus on the case that there is no Majorana zero mode. Then every defect actually comes with 2 kinds. One is a G0, and the other is whether there is a fermion stuck on it or not. So there are 2 kinds of defect. They differ by a fermion. Okay, that's a more detailed information of the detailed property of the defect G. Then this is roughly speaking, it tells the fermion parity on a defect. So now in these fermion systems, under fusion of defects, the fermion parity must be conserved. Okay. So the fermion parity conservation, suppose you fuse G not G0 defect and H0 defect, we must get a GH defect. So of course, in general, we should put lambda here, but let me split them into another one separately, trying to be clear that what it actually this N2 is. So this is basically saying that there is probably an extra fermion we need to add. Okay. so that the total fermion parity on the left-hand side and the total fermion parity on the right-hand side, they are equal. Otherwise, fermion parity will be violated. Okay, so this N2 basically characterizes how fermion parity is conserved in defect fusion. And in the previous case, what we were describing is how Majorana zero modes is conserved under defect multiplication, right? So now here is a fermion parity is conserved. And no wonder that you actually should satisfy some consistency condition by fusing 3 defects. And the 3 defects should satisfy associativity. That means that whether you first fuse, the first 2, then the third, or first the second and third first, then at the end fuse with the first one. So there are 2 orders. Okay, so they should be consistent. So this consistency actually gives another equation. The left-hand side is some combination of N2 that we define here. The right-hand side is some quantity that build out of this lambda and this mu. Okay, more compactly, mathematically, we can write them in terms of the so-called cup product, lambda, cup, and 1. So it may be less familiar to you, but it basically just means this expression. And this lambda 1, lambda cup 1 lambda is this whole expression. Then the left-hand side is the 3 co-boundary actually, because so we got this equation. So this equation is similar as the one for the Majorana zero mode case. The right-hand side, one can show that it's a 2 co-cycle, it's 3 co-cycle. The left-hand side is a 3 co-boundary. So there requires some, so it gives some consistency condition that we, in order for the system to be compatible with the symmetry. So in fact, there's another consistency condition which I don't have time to talk about. It's more complicated, and in fact, there are some paper. So our paper is kind of 1 week later than these 2 papers. We were trying to study this in forced symmetry breaking. These papers, they appear, so we kind of hurried up and finished our paper within a week. But this paper, the first paper, actually focused a lot on trying to derive the expression of this O4. So it's also a further consistency condition one needs to consider, other than the first 2. And in our paper, to be honest, our expression of O4 is not as complete as their expression. But these papers, they don't study the phenomena of enforced symmetry breaking. So they are so purposely trying to study all these consistency conditions. But what we were trying to do is find these consistency conditions and then solve these consistency conditions. And one of the most interesting solutions to these consistency equations are these incompatible cases. So with these consistency conditions in hand, okay, so now then we can state the sorry. Yeah. So we can state the criterion for even nu. GF is enforced to break by 2D invertible topology. Oh, sorry, here should be even nu. There's a typo for even nu. If and only if O3 is a non-trivial cocycle for any N1. So in this case, now we allow N1 to float. Okay, N1 is a variable. So if there's no N1 solution at all, then this symmetry is enforced to break. Or if N1, there exists some N1 such that this consistency condition is satisfied, then you go to the next layer of consistency condition. So then for any N1 and any, then for all N2, we should have, if this O4, which I don't show the expression here because it's very complicated, and if it's non-trivial focal cycle, then we have an incompatible case. Okay. Since I don't have, maybe I have a few minutes, so let me give you an example. So the simplest case for the even nu, okay, for odd nu, the criterion is simple. So the example is the same as the in 1D, that's Z for F. But for even nu, it's more complicated. We need to study this O3 obstruction. So this O3 obstruction, I was trying to say whether there are some physical argument that I can demonstrate, but unfortunately, sorry, I don't have some physical explanation of this example, but only a mathematical one. So, so the simplest example for the enforced symmetry breaking in this case is actually the quaternion group. This quaternion group is the group formed by quaternion numbers. So in that case, this G is actually Z2 cross G2, and we can denote them as 1 A B A times B, and the GF. So after we include the fermion parity, it's this. But the important thing is that and the original so this A B C D, so A square becomes, instead of 1, it becomes fermion parity. B square also becomes fermion parity, and the commutation relation, originally it's a abelian group, so they commute. So the commutation relation also, it gets multiplied by the fermion parity. So in order to study whether it's trivial or not, we actually computed the typological invariance, which are some mathematical quantities that is invariant on the co-boundary transformation. So and it turns into these 4 equations. Okay. So in order, so this O3 obstruction is trivial as if and only if all these 4 equations, all these 4 quantities, which are called topological invariants, are 0. Okay, modulo 2. Then you ask the question whether there exists any solution for this equation or not. In the case of quaternion group, these numbers are 1. So basically corresponds to these 3 equations. 1 means that it's P, and P. Okay, so then this becomes a simple algebraic equation. You ask whether there is a solution of N1 or not. So remember here, we have 4 equations, but only 2 variables, N1. N1 itself is a function. So this function is determined by 2 elements. The generator A, the value of generator A and the value of the generator B. Okay, so there are 2 variables and 4 equations. And in general, we expect that the solutions may not have solutions, and and this is indeed the case for the quaternion group. So so with all these criterions, we can go on, but it's just computationally not easy. These obstruction functions, the O1, O2, O3, O4, in particular O4 is very complicated. And in order to find examples that no solutions of N1 and N2 exists, it's not that easy. But for this nu equals 4k plus 2 or nu equals even, this case, I just mentioned this quaternion group. But if it's 8k plus 4, then we it's not that easy. We use a computer to find some example. It's order to, we don't even know the name of the group, so it's not that easy. But fortunately, we maybe if I have time, I will mention that we also find a family of model enforced symmetry breaking of a continuous symmetry group. At this moment, I only talked about discrete symmetries, because all these defects and kind of the picture are mostly compatible with are used for discrete symmetries instead of continuous symmetry group. But I will later maybe I have 2 more or more 3 slides to go. But before that, I want to say that I want to make a connection between this. So this table basically is a kind of a summary of what I've been talking about so far. Our purpose is trying to find all these examples beyond the time reversal symmetry, the enforced symmetry breaking example beyond time reversal symmetry. And indeed, we find all of these cases for 0D, 1D, and 2D, all of them. I haven't talked about 0D, but it's actually, we also did that. So I want to make, before I talk about this SUFN continuous symmetry group, I want to make a connection between this obstructions or this enforced symmetry breaking with quantum anomaly. So we all know that in the case of topological insulator, at the surface of a topological insulator, there's a direct cone. People say that there is a so-called time reversal anomaly. Okay, and in our case, we can actually state in a similar way that if you try to gauge the fermion parity, okay, insert the fermion parity defect, but let it move in the sense that it becomes a dynamical particle, then it's actually become a Z2 gauge theory, where you have 4 anyons, the trivial one, the fermion, and the fermion parity, which I denote as W here. And but with a remaining symmetry, that's the quotient group G. and with the condition that symmetry fractionalization on F is determined by this lambda. So all these obstruction functions that we were talking about can be stated in a way that it's actually associated with the quantum anomaly of this anion system. In other words, this quantum anomaly says that there is a non-trivial bulk, okay? Even though it's not that easy to state what this bulk is, but these obstruction functions, O2, O3, O4, characterize the bulk. And if the bulk is non-trivial, that means it's not a strictly two-dimensional system. It is a boundary theory. Okay, so that means if you think of that in terms of 2D theory, you're going to end up with some inconsistency condition. That are these conditions that I was talking about. But anyway, so that's a simple connection that I want to make. So now let me finish my talk with this enforced symmetry breaking of continuous symmetry group, SUN. So, so let me start with this SU2. Let me make a claim that this SU2 symmetry, if let me focus on the case that it's an even nu, because all the new case is simple. The even nu case, let me claim that. So for even nu case, that means it's actually an integer quantum Hall state, right? Because 2 layers of P plus IP superconductor is equal to 1 layer of integer quantum Hall. So it's actually integer quantum Hall. Then you can define a Hot conductance, okay? So let me make a claim that if this Hot conductance is SU2 symmetric, the whole integer quantum Hall state is SU2 symmetric, then the Hot conductance must be even. Intuitively, it's right, because if you think of this SU2 as spin conservation, then the integer quantum Hall state must have 2 layers. One is spin up, the other is spin down. Each layer contribute nu equals 1. So the sigma h equals 1, the Hot conductance. Then the total must be 2. Okay, it's even. But what I want to have is a more general argument. So this argument is actually not that complicated. So that's why I want to share with you. So consider adiabatically inserting a fermion parity flux W instead of so this pi flux. So or associated with this U1 symmetry, U1 particle number conservation. So first of all, we know the Laughlin argument. It tells that the Hot conductance is equal to the charge accumulated on a 2 pi flux that we insert. Okay, if we insert 2 pi flux, we got a Q2 pi. But this W is a pi flux, so the 2 pi flux, the charge on 2 pi flux is equal to twice of the pi flux. Oh, that's one conservation. But in general, so in general, Q2 pi, because 2 pi flux is actually trivial. You can gauge it away. It's gauge equivalent to with no flux at all. But this pi flux is not a trivial flux. So in general, this QW does not have to be an integer. It may be fractional. However, if this fermion, those particle number conservation is a subgroup of this SU2, so this is this U1 shouldn't be confused with the actual physical charge. It's actually the spin conservation of the Z component. So that means the charge is actually twice of the SD. But SD, we know it can only be plus minus 1. This twice is coming from the fact that SU2 has a periodicity of 4 pi, but U1 usually we use a 2 pi periodicity. So there is a periodic difference between them. So the charge also gets we multiply it by 2. So there is a difference. So once you combine this, then you can argue that this embedding says that QW must be an integer. Okay, so that means that sigma h must be, so once this is integer, sigma h must be even. So that means that if new sigma h is odd, SU2 symmetry is enforced to break, okay, because it's incompatible. This argument can be generalized to SUN, and the argument is very similar, except there are some extra things you need to consider. But then at the end, you get some equation, consistency equation, in order for the SUNF symmetry to be compatible with integer quantum Hall states. And then if they are incompatible, we got the example that enforced symmetry breaking occurs. Okay, sorry, I'm late for like a few minutes, but let me briefly summarize that we basically studied the phenomena of enforced symmetry breaking, and that is incompatible cases of topological order and symmetries. And we obtained some obstruction functions, and also discovered a few new examples of enforced breaking beyond the time reversal symmetry. There are quite a lot of open questions that we can study because we focused on the simplest case, that's invertible topological order. You may ask general topological orders and also time reversal symmetry of general topological order, compatibility between time reversal and the general topological order. Then also this conditional anomaly, it's actually something that people can think of, and also applications of this phenomena. I don't know whether there are any useful applications or not. With that, I would like to thank you all for the attention.
Okay, thank you very much. Do you have any questions from the audience? So maybe let me just start with some very general question first before going into specific ones, also for the benefit of the general audience. So, so we have a large family of so-called symmetry-protected topological insulators, where in these cases, the symmetry is a necessity. In a sense, the Hamiltonian has to have a symmetry for the topological order to be realized, right? So I suppose for these family of topological orders, you consider them as like trivial. You're not talking about this kind of topological orders in this particular work, right?
Yeah. So by topological order, I actually mean, first of all, it should be non-trivial in the absence of symmetry.
Right. So many body localized entanglement is like one of the requirements for this definition of the topological order. Yeah, and here you're talking about all the topological orders you refer to in this work are not symmetry protected topological insulators.
No, it's not symmetry.
Okay,
so you can think of symmetry protected topological phases as the enriched trivial phase, symmetry enriched trivial phase.
Yeah, exactly. Yes. Okay, so the second family of topological orders are the symmetry enriched topological order. So here, I think the idea is that for the Hamiltonian, for these topological orders, you can either have symmetry or not having symmetry, but it is still topological. But once you put into the ingredient of this symmetry, you can have sub-topological phases. Right. So example, for example, is actually the example I mentioned just now. If you have a strained graphene with a pseudo-magnetic field, since this is in some sense a symmetry-enriched topological order. If you do not consider symmetry, you have valley charge. But if you consider the time reversal symmetry, you can also have charge edge modes.
I would say this is still not symmetry-enriched topological phase. You are enlarging both before and so both of them. You just consider. I think you are. Let me see. You are considering probably different symmetry groups.
Yeah, I'm considering, for example, the time reversal symmetry. The topological order does not require time reversal symmetry. But if you put in time reversal symmetry with or the absence of time reversal symmetry, you have additional topological order with a new topological index, like the charge transform.
So what I mean is that you are considering two symmetry protected topological phases, but one of them has a larger symmetry group, the other has a smaller one.
I see, because this one still requires, in your case, the U1 symmetry. That's
So maybe I would say that so this kind of hierarchy of so you are let me state it in this way. So you are considering first you start with a small some topological phases with a small symmetry group. Then you have maybe phase 1, 2, 3, 4. Then you add an additional symmetry, say time reversal symmetry. Maybe 1, 2, 3 is compatible with time reversal, then it's gonna be enriched. You have more phases, you have an additional index. But maybe phase 4 is incompatible with, even though it's not topological order, it's symmetry protected topological phase. But this symmetry protected,
this is just a different. I see. Yeah, it's different ways of enriching a trivial topological phase in your language.
Yeah, different ways. But different ways, you may also have a compatible case because some symmetry protected topological phases is incompatible with an additional symmetry you are considering. So that's like what you would say is enforced breaking by some symmetry protected topological phase, not this topological order. So it's like even before and after you add an extra symmetry, you always have this extra symmetry add. You already have some symmetry to start with, and there are some compatible and incompatible cases.
So maybe another example is the Moritz state. Then the Pfaffian and anti-Pfaffian are symmetry enriched, I suppose. So they have the same Hot conductivity. Of course, they are topological, non-trivial topological orders. But if you put in particle Hot symmetry, then you have Pfaffian and anti-Pfaffian. Is that an example with symmetry-enriched topological order?
No, that's not actually.
That's not.
They actually belong to different topological order because they are thermal Hot conductance are different.
Okay.
So it certainly it depends on.
I see. So for the symmetry-enriched topological order, all the topological indices have to be the same.
Yeah. So
they only have different symmetry. Okay.
Yeah. There are different people, you know, depending on how you in what context you are talking about. So, but most, at least for me, so you first fix all the topological properties like anion braiding, thermal Hot conductance. Okay, once you fix that, then you add a symmetry, and the symmetry enrichment may be different. This difference appears, for example, a given anion may carry different fractional charge, maybe 0 or 1/2. So that belongs to different symmetry-enriched topological space. But what you are talking about is two different topological orders. This Fermion and anti-Fermion. They have different thermal Hot.
So if you have fractional charge with different, the fractional charge itself is like a topological order, right? So
the fractional statistics is topological order. Fractional charge is a symmetry. It's a symmetry property. So this Fermion, anti-Fermion, without I think it's for people from reality. You always start with system with symmetry, right? So you have you can talk about fractional charge, but actually this fractional charge. Suppose you write down this Moride wave function, this Fermion state. You write it down. Right. You can add some perturbation so that the fractional charge becomes meaningless.
Well, actually, that was another question I will ask later, about this U1 symmetry in fractional quantum form. But I get your point. So basically, you're saying that for two symmetry-enriched topological faces, all topological indices have to be the same, but the symmetry of these two faces can be different. So that's the idea.
Yeah, that's one way to state the problem.
Yeah. So I talked about two family. One is the symmetry is a necessity. The second family is symmetry is an optional. Then the one you're introducing here is like the third category where the absence of symmetry is a necessity.
Yes,
or exactly. This incompatibility between symmetry and topological order. So what you're implying is, for example, if I want to realize this topological order using a Hamiltonian, then this Hamiltonian has to explicitly break that symmetry. Otherwise, you can't realize this topological order, right?
Yeah. For example, so maybe what you are thinking is some possible application, like how useful this, because what I'm talking about are some formal results.
I'm trying to go in there. Yes.
so what kind of application you can think of? So
before you go that, maybe Chenjie, before you go that, can you illustrate this? Because a lot of you introduce is very interesting formalism, but also quite formal. So before you go into application, but can you go back to this 1D Kitaev chain? So this is an example of the absence of symmetry is necessary, right? You gave a very general proof mathematically. So if I go back to the Hamiltonian, what kind of symmetry do I have to break with my Hamiltonian physically in this particular example?
Particle number conservation must break.
So it's just U1 symmetry that you're breaking here. The pairing will break the symmetry you're talking about here.
Yeah, but must break down to the usual Z2. So for example, this Z4F, you may still have this Z4F in the sense that it's instead of a charge 2 superconductor, it's a charge 4 superconductor. So, so this example can be stated in more regular language is that you cannot have a charge 4 superconductor that supports Majorana 0 mole.
I see. Yeah. Okay.
So that's one way to state that.
Okay, great. Thanks. I think I've asked enough general questions. Any questions from the audience? Any comments? Since it's still, I think the language here is a bit formal, so I think maybe not easy to follow for many people. Questions? If not, I'm going to follow up with some more specific questions or discussions.
Sure.
Yeah, so if we go back to the U1 symmetry in fraction, okay, first of all, the integer quantum Hall effect is a topological order in your definition, even though the ground state is a product state. And but it does not
it's not a product. Actually, it's not integer quantum Hall.
Yeah, depending how you look at it, you can't really disentangle it, right?
Yeah.
But in orbital basis, of course, it's not very different from the single particle topological insulator.
That's true.
Yeah. Okay, so for fractional quantum Hall effect, normally we say the fractional quantum Hall effect does not require any symmetry. And of course, we don't really require U1 symmetry. You are saying here U1 symmetry is one way to enrich the fractional quantum Hall phases.
Yeah.
So normally we also consider the fractional charge as a topological index because it all comes from the Hall conductivity, right? It's about inserting the magnetic flux. Then the charge is computed from the Hall conductivity. But normally it does not require U1 symmetry as well, because if you break U1 symmetry, the Anderson localization will still take care of it. As long as you are at the plateau, the charge of the fractional of the quasi holes or these anions are still robust. Right? So can you explain a little bit about this U1 enriched symmetry in fractional quantum Hall systems?
So first of all, when you say you are off, localization, that's translational symmetry. That's not particle.
Yeah, we do not require any translational symmetry, right? If it always, even if I don't need a disorder, I still have a boundary which breaks the translational symmetry.
Yeah. So what I'm talking about here is particle number, just the usual particle number conservation.
Right. So without particle number, the Hall conductivity is still robust in experiment, right?
Yeah.
And if the Hall conductivity is robust,
no. Hall conductivity can be defined only if you have U1 number conservation. Otherwise,
yes,
you can't even.
Yes, formally I agree. But the thing is that normally in fractional quantum Hall, the reason why we can see this Hall conductivity is because of plateau in the experiment. And this plateau means if I break U1 symmetry, if I move a little bit away from the center of the plateau, the Hall conductivity is still fixed. Right? That's coming from the localization effect of these quasi-Hall, quasi-particle excitations. So that's another argument in saying that the fractional quantum Hall does not require U1 symmetry, because even breaking U1 symmetry, the Hall conductivity is still robust.
I think you are talking, I'm not sure if that's true. When you are away from the plateau, you're still on the plateau, but you break U1 a little bit, it's still robust, but only this kappa XY is robust. Instead of this,
if kappa XY is robust, then the fractional charge is robust.
No, there's no obvious connection between kappa XY and the fractional charge.
The fractional charge is computed from kappa XY. Kappa XY means sigma XY, right? That's the Hall conductivity.
Yes. No. Yeah. Kappa XY is thermal Hall. Thermal Hall is only.
Why? Okay.
Sigma XY is a electric conductance. Charge conservation. Yeah. Charge conservation is coming from you couple the system to electromagnetic field. Electromagnetic field is your U1 gauge theory.
I see. So here you're talking about the particle conservation.
Particle conservation. Yeah, nothing fancy. It's just the usual particle number conservation.
Yeah, but this now particle carry a charge. So particle conservation and charge conservation is the same thing, right?
It's the same thing. It's the same thing.
So that's still, I'm saying that if you go a little bit away from the plateau, the fractional charge is still robust, because the fractional charge is computed from the charge conservation.
No,
not charge conservation, computed from the Hall conduct, the sigma XY, right? Sigma XY is robust.
What I'm saying is that fractional charge, sigma XY, they can't even be defined without particle number conservation.
Well, formally I agree, but the thing is that normally the way we understand it is that if you break U1 symmetry slightly, then it will not affect the topological indices because
that I agree. But that's there is a assumption here is that if this quantity is, you can still define it, then you add some perturbation slightly away from the state, the value cannot be changed. But the current cases you are talking about is this quantity can't even be defined.
I'm actually talking about the first case, starting with Hamiltonian with all the symmetries you want. But the thing about these topological orders does not require any topological symmetry protection. Is that starting with the Hamiltonian with all symmetries you have, you add the perturbations, break any one of the symmetry, the topological index should always be robust. That's I think a definition from a Hamiltonian point.
So for example, so how you define sigma XY, right? You define sigma XY is that because you started with the system that has the particle number U1 conservation. So you define sigma XY by couple it to electromagnetic field, right? Then you compute using Kubo formula or something like it. Then you compute the sigma XY. But but without U1 conservation, there is no U1 gauge field. There's no magnetic field. So you can't couple it. Then you can't compute sigma xy.
Yes, but if I add a perturbation that breaks U1, it's still fine.
I think there's some logical issue here.
Some subtleties.
Yeah, some subtlety. So there are still something you can compute, but that's maybe the value is the same as sigma xy, but it's something else. Yeah.
Okay, so from experimental point of view, of course, I can introduce some perturbation. What I measure, either for sigma xy or the fractional charge, they're all robust. So from this particular point of view, effectively speaking, U1 is not required. Just like the case when you say time reversal symmetry is not required for those topological order not requiring any symmetry protection. Normally, you can also interpret it as if you add a perturbation that breaks symmetry, nothing will happen, right? Unlike those symmetry protected topological phases, you add a symmetry breaking perturbation, the topological order goes away. Right? So the gap will open at the edge. Right?
I don't know, like maybe you want some numerical way to check this. For example, if you have a fractional quantum mode state, you add a superconducting like CC, CC term.
Yeah, you can add a
just as usual one.
Yeah.
I don't know, like how do you compute the Hot conductance?
For the pure Hamiltonian, yeah, it will go away. But if you add disorder, then
no, not disorder. There's a pairing term.
I know. So even experiment, right? In experiment, you can add any pairing term you want. You're just moving away from the plateau, but you're still on the moving away from the center of the plateau, but you're still on the plateau. So from that. But I agree with you. So for example, if you're studying with a numerical with a pure Hamiltonian, adding a small U1 breaking perturbation, you add even a single charge to the system, the fractional charge will change by a small amount, right? But that small amount is also going away in thermodynamic limit, because it's really just it's just a filling factor, right? The fractional charge is just a filling factor. So adding one charge to it, changing the filling factor by a little bit, but in thermodynamic limit, the fractional charge is still robust.
Okay.
If you break U1 in this way, right? I can remove or add a few particles. I'm changing the charge from 1/3 to 1/3 plus 0.000001, and that small perturbation goes away in the thermodynamic limit.
I guess we can take more. Like for example, you use some language like filling factor. I don't even know how to define filling factor.
Oh, filling factor is sigma xy. So that's
sigma xy. So
yeah, sigma xy. Sigma xy is from Lorentz invariance is basically the filling factor, the density of a charge in the sample.
Okay.
Yeah. Okay. So anyway, so this is one thing that I was a little bit puzzled about. Okay. Any other questions from the audience? Any comments? Okay, so if not, maybe I can discuss with Chenjie privately with some other questions. You are welcome to stay if you want, of course. Okay, so let's thank Chenjie for the very interesting talk, and yeah, thank you everyone for attending.
Thank you.
Thank you.